So we're going to be talking about emojis, 10 ways the poo emoji can break your app. But just a couple of things. First of all, emoji support is important. Users kind of expect to be able to use emojis nowadays, but also really what I'm talking about here is, does your app support foreign languages? Does your app support all foreign languages? So we're talking about emojis, but we're also talking about foreign languages. Another thing is that this is async, so all of the examples are going to be in JavaScript, but most of what I'm talking about will apply in most other programming languages. So hopefully there should be something for everyone. So we're going to jump straight in. Anyway. Okay, so, yep, is that okay? Can I remove that? It doesn't matter. Okay, so we'll go in straight for number one. So you want to use regular expressions. If anyone in the room hasn't picked up regular expressions yet, I'd really strongly advise it. I found my old regular expression book. This is the book I used to learn regular expressions. It's tiny, and in my day-to-day job, I probably use about half of it. So I'd strongly advise learning regular expressions. But effectively, what regular expressions is we're doing pattern matching. So in this example, we have this string, how shit is JavaScript? And it's a valid question. And this is the pattern that we're trying to match. And in the world of regular expressions, a full stop is supposed to be match any character. So if we think that the poo emoji, as far as our computer is concerned, is just a character in a foreign language, so we would expect this to work, but it's returning false, which we don't expect it to work, even though JavaScript isn't a shit language. So let's just jump straight to the answer. If you add the U flag, that's going to work. What the U flag is doing is it's saying, I want extended Unicode support. It's very easy to say, but then that just raises the next question of like, what the hell is Unicode? And if we think about a string, which is our string here, hello poo, and we pull back a layer of abstraction, really what the string is just an array of numbers. So here we have our characters in an array, and here we have those numbers that represent those characters. So each character that you'll have in a string will have what's called a code point, and this is represented as a number. So really we're thinking about arrays strings as arrays, and this is why in lots of programming languages, most things that you can do on an array, you can also do on a string, or they're array-like, they implement iterable depending on the language that you're using. And it's because under the hood, really, that's what it is. It's just a bunch of numbers. So what Unicode is the map, or part of what Unicode is, the core part of what Unicode is the map that maps these numbers to the characters. So here we've got the character H, which is the number 72, and the standard in Unicode is to write these with a capital U, and then to write the number in hexadecimal format. So we've got here 72 in hex is 0048, or just 48. If you're a front-end developer and you're not used to seeing hexadecimal numbers, we normally see these in like color codes. So like FF is actually 3 numbers. But throughout the talk, I've got some of it in decimal, some of it in code points, often both on the same screen, just because it's a bit easier to wrap your head around. And straight away, we can see that one number is not quite like the other one. This is fantastically larger than our H or our H or our exclamation mark. So let's have a little look around what Unicode is. And where are we? Okay, so this is a little app that I made that just prints out all of the Unicode characters. Unicode is arranged into what's called planes, which are kind of like chunks. So each plane has about 65,000 characters in them. The reason it's this number is this is the highest number that can fit into 16 bits. So if we have a little look around Unicode, first of all, we see the familiar Latin characters, uppercase and lowercase, the kind of characters that we would expect to see on an American or English keyboard. And then as we go down, we get into the more kind of European characters. So we've got like umlauts, we've got E's with accents, kind of French characters. But one thing to get your head around is that Unicode is big. Like it's really, really big. We've got Arabic characters here. We've got, scroll down, we've got Chinese, Korean, Japanese. So this is the Han Chinese set, and this goes on for a long time. There are a lot of Chinese characters going on here. So one thing to note about Chinese characters is that they are, whereas we make up words by joining letters, which each letter is a code point. In Chinese, obviously this is a word, and each word will have its own code point. So this is why there are so many of them. They've effectively taken their entire dictionary and put it, each one having its own code point, put it into Unicode. There are loads of other things in Unicode. So we've got here Braille, if you wanted to print out Braille. We've got kind of technical mathematical symbols. If you have a particular field of research, like advanced fluid dynamics or something, and you may have a symbol that makes sense to you, it will be in Unicode, even if no one else in the world really knows what it means. So it's huge. And the idea of Unicode is that it's going to be a character map of every visual glyph or character that any human today speaks or uses, and every human that has ever lived will speak or use. So there are also characters there for effectively dead languages. So if we move along to the next plane, this is a supplementary multilingual plane. We've got things like Egyptian hieroglyphs. This is in Unicode. If you want to text your friends in hieroglyphs, you can. Your phone supports Unicode. You can send text messages in hieroglyphs. We also have languages that we don't understand. So here's a language called Linear A. This is from somewhere in the Greek islands, I believe, and it's like an ancient language that we've kind of discovered tablets, and we found these characters on some tablets. We have no idea really what these characters mean, but they're in Unicode, and I guess this is important for people that are researching these things. So it covers every character that every human today will understand, and every character that every human that has ever lived will understand. So that's the scale of what Unicode is trying to do. And you can see here in Linear A, we've even got these square blocks. These are empty spaces, and they're waiting in case we find some tablets in a cave somewhere that have some new characters that we don't know about. They're going to go there. And finally, so on this second plane, these are emojis. So these are implemented just as if they were characters in a foreign language. And we can hover over them, and each of them will have their own code point. So that's the Unicode map. Let's go on to reason number 2. And before we do, reason number 1, regex, you're kind of going to get an understanding of why that didn't work as this talk goes on. So that's why I haven't kind of closed that off. So reason number 2, you want to use sort. So imagine you're going on holiday and you write out a list of places that you want to go and visit. Pupu Land, this is a real place in Korea. You can visit it if you want. It's a theme park, an amusement park, I believe. We've got Disneyland, Uberhen, Dubai, Machu Picchu, Zurich. And just take a moment to think about the standard sort method in JavaScript and what we would expect that function to do. So we're trying to sort alphabetically here. So if your answer was anything like this, then you know JavaScript very, very, very well. Okay, so this is a little bit crazy, right? This isn't sorted alphabetically as we would expect. But what's really going on here is that the standard sort is sorting it by code point number. So this is why we have uppercase first, because the code points for uppercase come first in the character map. Then we have lowercase, then we have the kind of foreign, the German characters, and then we have emojis, which are all the way in another pane. There's a solution to this. So Unicode, the consortium published the character map, which is the mapping between the code points and the characters, but they also publish a bunch of other things, and one of them is the collation algorithm. And this is a specification. It's about 20,000 lines long of text that defines how these characters relate to each other, how they order, how you order these characters. And the good thing about Unicode publishing this is that our implementation in JavaScript is called locale compare, which comes off the back of a string, but you will be able to find your implementation in the language that you use, and hopefully it should spit out the same results. So this is a bit more sensible. We're doing essentially case-insensitive sorting. We've got Z right at the very back, which is what we'd expect. For some reason, Poo-Poo Land has ended up as the first in our list, so obviously that's where we want to go on holiday. Before we go on, really I put this question in for Jake. What do you think that's going to do, Jake? Just to pick on you in particular.
Is it going to be 1, 2, 4?
No. It's JavaScript, of course. That's what it's going to do. So the sort is, by default, without providing anything to sort, sort is for sorting arrays of strings. So JavaScript will very kindly convert these numbers into strings. It will then sort on the code point of those of the characters, and this is why all the ones come first, and then the fours, and then obviously a very simple solution to this, but it's just JavaScript is a little bit crazy. Yeah.
I thought you were going to have a character that looked like one of those numbers.
Everyone said that was what this talk was going to be about, but I haven't put a single example of that. What Jake is talking about is that in the character map, we saw it was really large, and some characters have different meanings, but look visually the same. So I think one example that Steve found was a Russian Z, was that right? Looked the same as a Latin 3. Yeah, so visually they look the same, although they're different code points. That is not in any part of this talk, so any time that I'm trying to trip you up, that won't be the answer. Speaking of which, yeah, what's gone wrong here? Because that's exactly what could have gone wrong here, but that's not what went wrong here. Yes, Tom, bloody hell. Yeah, so this is how this talk came about. I'm not like preaching from a high place like I know everything about Unicode. Basically, over the years, a bunch of bugs have come my way, and I've had to learn just a little bit enough to kind of figure out how to fix that bug. And this wasn't one of them, but this is an interesting thing. So, okay, number 3, you want to test for equality. This is a really important thing for us to be able to do. If we can't do this, then we can't do our jobs. We do this day in, day out. So I'm not talking about characters that look the same, but that are different code points. I'm not talking about white space, zero width white space characters. There are some code points that take up no space that could just be hidden in your string. That's a particularly good one. If someone leaves their computer open at work, you go in and you put that in their code, it takes them hours to find out what you've done. Brilliant. I'm talking about the E with the accent. So, but to extend the problem with quality is this impacts a whole bunch of other things that we want to do. We want to do includes, can't do that, can't figure out, can't do index of. Filtering, searching for things, like day-to-day bread and butter things that we do to build very, all the software that we use, that we work on. Really important that this works. So obviously I've zoned in on the E with the accent. And let's have a little look a little bit closer at the E. That's a little bit confusing, isn't it? So to us, and this is one thing that comes up that is going to be the core of lots of problems. To us, Latin, who use the Latin alphabet, for us, one character will equal one code point, will equal 1 byte of memory used. And those 3 things are just not true outside of Latin. So here we have the E with the accent, that is 1 code point. Here we have the E with the accent, and for some reason that's given us a length of 2. And the reason is that it's actually 2 code points pretending to be 1. So there's one way of doing it, the E with the accent, that's code point 233, the regular Latin E, which is 101, and the acute accent, what's it called, modifier, I think, modifying character, and that's 769. So this character is very special because wherever you place it in your string, it's going to jump onto the top of the previous character. So these, the 2 characters have the same meaning, but there are 2 different ways of building them. Jake? I think you should be able to, can you not? No. It's definitely something to try. Yeah. Well, funny you may mention that. So before we move on, this is just a notation for writing Unicode characters in string. So you /u and then the Unicode code point. So that's what's going on here. E and the character. And obviously, as soon as you create that, someone is going to be mischievous and just carry on adding them. So to be clear, this is a nonsense character. This doesn't exist in any language. This doesn't make any linguistic sense, but the renderer is perfectly happy to say, yep, I'm just going to carry on adding those. So number 4, thank you very much, Zalgo text. I've put this as a way that, well, this isn't a poo emoji. All of the other examples will be poo emojis, don't worry. But this is a way that it can break your app. For us front-end developers, normally it's just a visual thing. You know, we have this presumption that a letter is going to be a certain height. And Zalgo text is where we just added a bunch of these combining characters and created these kind of nonsense strings. There was something on iPhone where you could send a certain string and it would crash the iPhone. So that kind of counts, I guess. But yeah, it's a bit of fun. To the point where most systems just don't care. If you want to do that, no one's going to sanitize that away because it doesn't really cause that much of a problem, unless you're an iPhone, of course. Okay, so back to our original example. We want this to work, and as Tom said, you normalize it. So normalize is, again, effectively it implements a bunch of algorithms that are provided by Unicode. So again, Unicode Consortium is not just providing the character map, they're also providing us with a bunch of algorithms and attributes on characters that tell us if these characters can be exchanged with each other. The really important thing to note here is that these two strings have the same meaning. So this E is the same as this E in terms of linguistic meaning. So when you normalize it, the default in JavaScript will reduce it down to the few least number of code points. Yeah.
So we did triple equals
No. So the triple equals only stops it from doing type conversion. Yeah. So they're just strings. Yeah. So this is going to convert things that have the same meaning into something with the lowest number of code points. It's not going to do things like characters that look the same but actually have a different meaning. There is something. Yeah. No. So yeah, so we're reducing it down. So we have a two code point string here. We reduce it down to the single code point, which is the length here. There are a bunch of different options that you can pass in to normalize. Probably the most notable is, I forget what NFKD stands for. I should have had it in my notes. But what this is going to do is things that, to a certain extent, could be exchanged for each other. That's a very loose way of putting it, incredibly loose way of putting it. But so the example here is brilliant. You've got a CO2, which is the kind of the scientific notation, I guess, but you may have a document with that in it, and then a user's typing in a search, and they would type that, and they would expect to see that. So that's where you could use this kind of normalize. Doesn't strip out zero width characters, doesn't help you with characters that are different but look the same, but it kind of gets there. Okay, reason number 5. Accessing a specific character. This particular example, we do this a lot as front-end developers. We might have something like a profile picture placeholder that has your initials in it if you haven't uploaded a placeholder. It's a really common thing to want to try and access initials. So what we've done here is we've got a first name and a last name, and we're accessing the first name. This is a typical developer thing to do. We are treating this string as if it were an array. We're thinking that this string is an array. So we're trying to access the first character by accessing essentially the first code point. This works brilliantly in Latin, but imagine someone's come home from their holiday in Korea and they're feeling a bit cheeky, so they put their first name as Poo Poo and their last name as Land. What would we expect to happen in this scenario? Like ideally, hopefully, yes, Jake. We were talking about this yesterday, so I know that you know the answer. Yes, very good. Yeah. Weirdly enough, on my other app, it renders differently. I think it's the font that's doing it. Yeah, so we're not pulling out one poo emoji, which makes absolutely no sense. It's that we'll get to it. So if we look at it and we ask what is the length of the poo emoji, it's saying 2. And if we go to Unicode, how do I get rid of this? Can you? Oh, right. Okay. So if we go over to the Unicode website and we have a look, yep, the poo emoji, there it is. It's a single code point. So there's a single Unicode code point for the poo emoji. So why is it giving us a length of 2? Because it's the number 2. Unfortunately, to answer that question, we're going to have to go a lot more low level than we normally like to async and in JavaScript world. So remember how I said that a string, if you pull back a layer of abstraction, all we find is an array of numbers. What happens if you pull back a layer of abstraction from an array of numbers? Unfortunately, like all things with computers, you end up with just a bunch of 1s and 0s that are pretty incomprehensible. So these are the binary representation of 104, 105, 32, and whatever that number is. So this is that array, but in binary form. We don't like low-level programming. Things get very messy very, very quickly. One of the things, challenges that you're going to have with this, like to me, this is just an incomprehensible string of 1s and 0s. It's not immediately obvious to me where one number ends and the next number begins. There are a bunch of different ways you can do this. This is problematic. So how do we know? How do we encode these 1s and 0s into numbers? And unfortunately, with Unicode, there are actually loads of different ways that we can go about this. And this is the source of a bunch of problems. So by far the simplest way of encoding Unicode code points into binary is, oh, can't see the title. This is called UTF-32. So UTF-32, the naming convention here, the 32 means that for any character, for any code point, the smallest number of bits to represent that code point is 32 bits. So the way this system works is this is the simplest way of encoding Unicode code points, and it's just every code point takes up 32 bits. So this top one is the H, 104, next down is the I, next down is the space, and the final one is the poo emoji. So UTF-32, the simplest way of encoding Unicode code points. One problem with this encoding system is that if you're mainly using just Latin characters, so the lower number code points, you've basically got loads and loads and loads of zeros here. And if you think about what we're using these strings for, we're often sending them over the internet, we're saving them to a disk, it's taking up loads and loads of space, and it's kind of redundant, right? So there are other ways that we can encode these code points. So here's the one you may have heard of. This is UTF-8. The name here stands for, represents that, or tells us that the smallest number of bits to represent a single character is 8. So I promise you, we're going to get out of low-level code very quickly. So here we have our H, that's 8 bits, our I, that's 8 bits, space, and then finally the poo emoji, which is taking up loads and loads and loads and loads, 4 bytes. It's not particularly important to understand the mechanism of how UTF-8 is working, but the main thing you have to get your head around is just we've gotten rid of all the zeros. This is by far the most efficient way of encoding Unicode code points. It's so efficient, it's become ubiquitous. This is the most common way that Unicode is encoded and transported and saved to a disk. So if you're calling an API, it's going to come down as UTF-8. If you're saving something to a disk, by default, it's going to be UTF-8. It's so ubiquitous that often you'll find people talking about UTF-8 when actually they mean Unicode. It's a bit like the difference between the internet and the web. Like it doesn't really matter, but there is a difference there. This is used by everyone. Is this used by JavaScript? No, of course not. JavaScript, for some reason that boggled my mind and is the reason that I wanted to do this talk, uses something called UTF-16. So UTF-16, as the name suggests, the smallest number of bytes to encode, smallest number of bits to encode a character is 16. So here we've got the H, here we've got the I, here we've got the space. And then for our poo emoji, that's a number that's too big to fit in that space. So we now have 2 code points that have just come out of nowhere. So this is actually what a UTF-16 string looks like. So we have our regular code points, but our poo emoji is 2 code points. And these are the surrogate pairs. We're almost out of low-level land, don't worry. So surrogate pairs, 2 numbers to make one number of our poo emoji. And an important thing to understand about this is that this isn't just we're adding this number and this number to make this number. There's a little algorithm that is published by the Unicode consortium where you can take these surrogate pairs and you pass them through this function and it will give you an output. Not only are these 2 surrogate pair numbers not just numbers that you add together, they also know what order they should be in. So the high surrogate pairs should always be first and the low surrogate pairs should always be second. You can't reverse these around and get the same thing. It's not like taking 10 and 5 and adding it together to get 15 and then inverting it to get 5 and 10 together to get 15. You can't do that with these surrogate pairs. Just to hammer this one home, if we go back to our code map, scroll down. So these are all our surrogates. All of these question marks are surrogate pairs. So there are loads and loads and loads of these, and we combine them to make a new code point, which is on a different plane. So remember, this first page is the basic multilingual plane. And if we want to access code points that are on any of the other planes, we have to do it in JavaScript by using these surrogate pairs. And because our poo emoji is on our next plane, that's the reason that we ended up here. Individually, if you print them on their own, it doesn't make any... Sorry, Jake.
Can you mix any of those surrogate pairs together as long as they're in the correct order to create a character?
Yeah, any high surrogate pair can be mixed with any low... Or any high surrogate can be mixed with any low surrogate, I think.
That doesn't mean the code point you're going to get is going to be anything.
Yeah.
So it might be a nonsense character still, but it's a character that's somewhere.
It's going to be
Yeah.
it just might be in the last
Yeah, okay, so if we look at our...
created areas.
Yeah, if we look at our map here, so...
You still get a code point, but that code point doesn't necessarily be a character.
Yeah. So here, most stuff is in the basic multilingual plane. Emojis and a bunch of Chinese characters and stuff are in this second plane here. This is one app. The reason that I've done it in 2 tabs is it takes so long to render 65,000 divs that it's just easier. So there are some things in this, which is I forget the names off the head, but from here to here, from I think 4 to 13 is just void. It's just an empty space. There's nothing there. There's I think 14 and 15 is like a private use space or something like that. But yeah, if you were to just come up with a random number and try and get a glyph out of it, you're probably going to end up in like no man's land, like around here. So yeah.
One incredibly important detail.
Yes.
The planes above the basic multilingual plane usually referred to as the astral plane.
The astral plane. Well, that was is it a pejorative term? So when Unicode version 1 came out, it was just the basic, and then version 2 included all of these. But people kind of thought, well, we're never going to need them. So it's like, it's the astral plane. It's out there in the never, never. Like, let's not worry about that. And it's like was it IBM that said, oh, we're only going to need 4 computers? You know, so it turns out we did need them, and now this is where all of these bugs have come from. It's that mentality of never going to need it. Yeah. So let's go back to our problem. So we're trying to split out a name. We're trying to get the initials of a name. One way to solve this is to spread this string out into an array using the new spread operator, and that is going to take account for surrogate pairs. And then you can just, if you want to treat it like an array now, you can pull out the first version. So that brings me nicely on to number 6. This thing's getting really annoying. Ah, should have done that the whole time, sorry. Okay, so number 6, you want to iterate over a string. So we've seen that we can spread a string out, and that kind of handles our surrogate pair problem. Let's go through some of the ways that we would iterate over a string. So full on old school, for loop, and then we just log out the index. That's got all of the problems. So we've got our combining character is coming out and our surrogate pairs are coming out individually. That's not working. For in, exactly the same problem. For of, it's correctly outputted our poo emoji. So for of handles surrogate pairs. These things aren't interchangeable, which is a bit surprising to me, I think. What have we got here? So when we want to turn an array into a string, often what we'll do is use split. So this is where we just split an array and use a empty space delimiter, and that will break it out into an array. That doesn't work with any of these characters. New array from does work. Yeah, it's combined on with the, yeah. And our spread operator, and that does work for these surrogate pairs, but for all of these examples, the combining character doesn't work. So, yeah, if we look at these from the top, we can see the kind of the common characteristic of the ones that do work and the ones that don't are that these are all the ES6 things. These are all the newer things. So the newer things handle surrogate pairs and the older things don't, which may be surprising. It's surprising to me because I'd kind of thought that I could swap out a for in for a for of and it'll be fine. Yeah.
Is there time for oriented towards objects and arrays for of and
What was the question?
Isn't it that they're for in and for of are more oriented towards objects and arrays?
Oh, right, okay. Is it?
I think it's just that
The way they express it.
Emoji didn't exist when JavaScript was made. When it was made, so that's just how it works.
Yeah, the first version of JavaScript didn't use UTF-16, 32, whatever. It used an older version of encoding that was basically 16-bit and didn't include the surrogate pairs. So it doesn't have any concept of surrogate pairs. It's only the newer things that have a concept of surrogate pairs. So yeah, so we can solve this by just combining our two little tricks. Right, having said that, you want to use length. We've created this weird little thing that kind of solves all of our problem, but it really doesn't solve all of our problems. So consider that an application almost always isn't just a JavaScript front-end application. Normally we have layers in our system. So a standard kind of CRUD app would have a database, an API, and then some React or something living on the front end. Now, the really interesting thing about length is that the different layers of your application may have a different understanding of what length means. So if you think about a database, not all, but most databases are mainly concerned with how much space do I have to allocate on the disk for this column or this thing. So if I have a column and I say, well, this is going to take up 4 bytes of space on your disk. We now know that 4 bytes, that can be 4 Latin characters, or it can be 1 poo emoji. So what does length mean in the context of a database? Same as with the API. Different languages may treat strings differently, depending on if they're newer languages or if they're older languages, or what their level of Unicode support is. It's not just combining characters and surrogate pairs. It's going to get way more wild later on. So there may even be a newer language that comes in the future that handles these things much better than say Swift does, that's notoriously good at handling strings and emojis and things. And then when you think about your front end, really, what are we using length for in the front end? Often we've built a feature which is, I have a database field and I know I'm Twitter and I've got 127 characters. I don't tweet. How big is it? Something like that. Is it? Ah, they've taken away everything. Okay, so, but often the reason that we implement this is we have a text input and it's going in a database, and we know that that database is constrained to a certain length. So as people are typing, we're going to tell them, you've typed too much. Now the problem there is that your database may be thinking about a different length and your user may be thinking about a different length. If they type in the poo emoji and suddenly their count goes down by 2, that doesn't make a lot of sense to a user, but then how are you squaring that circle? Because you've got to make these two sides talk to each other. Okay, number 8, you want to truncate a string. Again, this is a really standard thing that we do in front-end world. Often we'll have a message and we want to see a preview of it. And you can see here, we've gotten really, really unlucky. Normally yep. Sorry? Well, imagine you had a blog post, would you, and you had a list of all your... So you would print out the entirety of your blog post. You could do that, yeah. And actually that would work, it would handle it much better than we do, sorry.
No,
With the ones that I played with, yeah, because I did have this exact thought, but there are more complicated emojis that we're going to talk about at the end that I haven't tested it with, so I have a suspicion that it wouldn't work for those newer style emojis. Let's just do that thing again and see if that works, sort of. This, really what I'm saying here is if you're going to normalize as things come into your app, don't just sprinkle this all over your app. And if you're gonna start treating a string as if it were an array, use the spread operator first, like you're going to get much better mileage. But this whole thing is going to collapse at the very end, so don't take this as like the way to fix anything. Okay, number 9, you want to reverse a string. Anyone here has ever wanted to reverse a string?
On a programming interview.
Exactly. No one in the real world has ever had to reverse a string, but for some reason this used to be pretty standard fare in interview questions. And if you Google it, the entire first page of Google is wrong and broken. Every single example is terrible. The most common example they'll give you is to split it into an array, reverse the array and join it back into a string. But we can see here what's happened. So our combining character has jumped onto the wrong thing, and our surrogate pairs are inverted, which means that they no longer work. Like it doesn't even point to like the wrong code point. It just knows that this is not correct. You could do that. Let's just chuck that in there and see if that works. If someone we were in an interview and showed me that, I'd be very impressed. So these are a couple of ways that we can solve these problems, but this entire concept is going to collapse when I show you grapheme clusters. So grapheme clusters, they're really, really interesting. These are the newer style emojis that have only come through in the last few years. So like support how we deal with these. We're still trying to figure out how it works. So this here is the family emoji. We've got mum, dad, little boy, little girl. We spread it out into an array, and what we find is that it's actually made up of other emojis, which is mind-blowing. I asked Tom for advice in this talk, and he said, what you should do is procrastinate and start building little apps. So that's exactly what I did. So this is a little app that you just type in here and it will give you kind of information about each character. So let's start with our poo emoji. It's very simple. One thing to note is that Unicode gives a character a name for every character, and that's almost the most important thing that they do. It's it sounds harsh, but they're not drawing these icons. You know, someone at Apple is doing that. It's the font's job to render the icon. What Unicode is doing is, for everyone, we agree that this code point equals this thing here. So let's have a look at, these were our combining characters. So we saw that an E and a combining acute accent made one character. But that's not the only way that you can combine things. So we have here a thumbs up sign, and if we want to have brown skin color, we just apply this modifier. So we have this afterwards. So again, you can see reversing that as a string isn't going to work at all. Some emojis, like we saw with the family, they're just built up with another emojis. So here we've got a dizzy face, and this is a special Unicode character. This is like glue. This glues two characters together. So I've got a dizzy face and a dizzy symbol glued together makes this emoji. Why not? I got carried away. There are loads of these. We've got we've got Santa Claus, we've got Mrs. Claus. If you want to make non-gender specific Christmas person, as you may do, adult joined with Christmas tree makes this thing. So you can also, we can take the shrug, apply a skin tone to it, join it with our zero width joiner to the female sign, and we change the gender of the shrug emoji to lady. Which means you can do interesting things. Bearded person with a skin tone joined with a lady. Bearded lady. Alistair. To be really clear here, it looks like, oh, I'm just like freestyling, mixing emojis together, and my computer is somehow magically figuring out what it is. This is someone at Apple has drawn that picture and said it is this, this, and this. So you can't just join. You can't do. This isn't magic. You know, you can't just take this and join any emojis and see what comes out. The family emojis are interesting because this is how the families are achieved, is that you can build up, you just join these emojis together to build up the kind of family cluster that you want. But like, look at the length on that. Like, we think that is one, whereas if you were to put that into Twitter and your character count goes down by 11, you're really going to notice that, right? So yeah, you can build up different kind of families. This one's quite interesting. If you want to do flags, there's a whole regional indicator symbols letters, which is a bunch of letters, and you just put your what's it called? The codes for each country. So USA would be joined together to make the American flag, GB to make the British flag.
They will have a base, so you can take the ASCII for G, add a number to it, which means you can just take the ISO characters for the country, add some numbers to them, and now you have the Unicode, which I've used before. It's amazing.
That is incredible. That's really incredible. Did you test it on a Windows machine though? Did it work? Okay. I got really excited, and I found that at the time of, like, I think it was a couple of years ago, it wasn't supported on Windows. I should have checked, because I really want to use this. It's so cool. Very aware of the time of this talk, so I haven't included it, but right to left characters and languages are a thing. If you really want to piss someone off, this is a string which is just async, and I've put this little cheeky one, right to left override, and it completely flips the string. How to reverse. If anyone asks in an interview, just Unicode 22E.
Such an amazing answer.
Yeah, I think it would really upset whoever asked it.
That's why I want to memorize that. Can you go back up to the question?
Yeah, sure. Okay, so graphene clusters, like, oh my God, how the hell are we going to deal with those? And the answer is, I don't. Most people don't. If you really want to, there is a brand spanking new thing in JavaScript, which is the segmenter on the internationalization library. I think this is new. I think this is ES 2022. Not 100% sure. It feels like it's been around for a while, but then lots of things are around for a while in Chrome. James Hugman isn't here, but the reason that I wouldn't use this in production is because Firefox doesn't support it. So, you know, maybe. And it's really ugly. It's really, really ugly and convoluted. The reason it's on the internationalization object is that it can change according to language, apparently. So one param you can put into the segmenter is what language you want to segment by, which is really confusing. Yeah, like if you really, 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 really care, then there you go. Oh, that's not true at all. Finally, so just to sum up, do use locale compare for sorts. I'd really, really recommend doing that. It's really important. Consider if .length is broken across the layers of your app. I definitely have apps in production now where that is broken, and I only found out because I did this talk. So, and finally, can a person use the name their parents gave them in your app? Which is a fair thing to ask. Like often we think we're building English language apps for English speaking people, and that may be correct, but those people may not have English as their first language. They may not have their name in Latin characters, and I think it's reasonable for us to support, you know, a person's name as their parents gave it to them. And finally, it's not there, but JavaScript is always going to be surprising.